All right, welcome to chemistry. Overwhelmed yet? Yeah, the organic chemistry has the ability to do that. Very quick note to anyone in distance learning. You do have a list of the videos we will be watching this chapter on page IV in your supplement. There are quite a few this chapter. We will be starting most of our classes with the video. So if you want to know what we're on, just look over the section we're going to be covering, and that will tell you. Seeing as today we're starting with 18.1, we watched video 40. So that's what we'll be doing today. Tomorrow we'll be watching video 41. Okay, all kinds of creative over here. All right, we do go a little out of order though, so just pay attention to that. We're going to jump right into organic chemistry. In case you haven't figured it out yet, organic chemistry is its own branch of chemistry. And when we say its own branch, we mean its own course of study. We mean its own dedicated scientists. We mean its own complete focus. Now, technically, the same thing's true with nuclear chemistry, but it's pretty easy to wrap your head around the basic concepts of that. Organic chemistry, we are going to, and I cannot stress this enough, give you a surface level knowledge of it. You are not going to be an organic chemist by the end of this. Okay? I am going to completely bypass swaths of knowledge because we just don't have the ability to cover that in 2.5 weeks. All right, so just understand that this is an overview. In short, though, organic chemistry is the study of compounds containing carbon. It's called organic because it was thought that anything containing carbon must come from life, and that was the only way to get it. Carbon is in group, I want to say 14. Yes, 14 of the periodic table, which means it has 4 valence electrons, which means it has a terrific amount of bonding potential. Consequently, that's why in some sci-fi universes, they'll try to use silicon-based life forms because theoretically you could, because it has the same type of valence electrons. Okay, it has that 4, you could just jump one down in the thing, and then it would be essentially incompatible with all carbon-based life forms, and so that's kind of their way of making a completely incompatible species. So that's the reason for it. It has never been observed, to be clear. All right, so just while I'm at that. Although, if it were to happen, it would follow all the same chemistry, just substitute silicon for carbon, and you're done. Not how anything we're going to do in here works. I'm just mentioning it as an aside here. All right, so we're going to jump right in here to this next bit. A couple quick things. We have limited it since its origin to say that carbon dioxide and many ionic compounds containing carbonate or bicarbonate ions are considered to be inorganic. That's just for clarity and to help limit the scope of organic chemistry. So carbon dioxide, yes, it comes out of us, but it's also produced naturally. So we consider that to be inorganic. Again, carbonate or bicarbonate ions, we studied those with acids and bases as far as neutralizing things with that. Those are also considered inorganic. For the most part, if it has carbon, it's organic, but those are the couple of exceptions, just for the sake of making chemists' lives easier, and those have very practical applications outside of organic chem, so they're kind of grandfathered into regular chemistry. All right, moving on. All right, now, first thing you need to know about organic chemistry. Far more chemical compounds are formed with carbon than with all other elements on the periodic table combined. There's 118 of them. One element versus 117 elements, the one element wins. It's weird, it's trippy, but it's true. All right, so this is the reason why it's its own branch. Now, organic compounds tend to differ from inorganic compounds in several ways. First of all, they tend to ignite or burn in the presence of oxygen or decompose in its absence. Okay? This is why you need oxygen in order to burn the fuel that you take in through food. Okay? You are taking in carbon substances, you're mixing them with oxygen, you are literally containing combustion inside your body in order to power your cells. There's no actual flame. Calm down. All right? But that is the chemical reaction. It is technically combustion. Okay, which is also why the theory is that, yes, we need oxygen to live, but it also slowly kills you because you're burning alive. There's that theory with it, but we're not getting into that. Okay, in the absence of oxygen, we say it decomposes because it obviously can't burn. Again, this was clarified in the video, but again, combustion means to be on fire. It does not mean to explode. That's a common misconception outside of chemistry. When someone says something combust, they typically mean an explosion. In chemistry, we mean it caught fire. It's a little more tame. A candle is combusting. Chill. All right? Now, with that, they also tend to have weak intermolecular forces, illustrated by existing in gaseous liquid or low-melting solid form. It's actually very hard to get solid organic compounds. You may have noticed this if you've ever done fuel, that doesn't sound right. If you've ever pumped fuel, you'll notice it's not a solid being inserted into your car, it's a liquid. And we're done. All right, moving on. Unless you're back east right now, and then you don't have any, but we're moving on. That's sad. All right, moving on. Where was I going with any of this? All right. Kerosene is another example. You'll notice a lot of it's fuel because we found out it burns real easy. Oil is another one that is in liquid form. If it's in a solid form, it doesn't stay that way for long. Examples of this would be butter or margarine. They're solid, but barely. Okay. You get them out in room temp long enough, and or in California temp long enough, it'll definitely melt. One of those things. So if it's in a solid, it's not going to stay there long. You have to keep it refrigerated, or it's liquid, or commonly a gas. Example of a gaseous organic compound would be the natural gas that comes out of your stove or that heats up your water heater. Those are all examples of that there. Organic compounds are mostly insoluble in water because they're mostly nonpolar. You'll notice I said mostly twice. There are exceptions. Yes. Huh? Barely. We have a solid outer layer. We have a lot of liquid inside. Moving on. All right, moving on. We're moving on. All right, these are mostly insoluble in water due to mainly being nonpolar, and our study on dissolving polar and nonpolar don't mix, hence why oil and water don't mix. Coincidentally, oil is an organic compound. All right, they have much slower reaction rates caused by the sheer number of covalent bonds. It actually slows down the reactions. This is why when we talked about TNT, I talked about how a stick of dynamite is about the same amount of energy as 2 candy bars. But if you eat 2 candy bars, you don't explode. You might expand a little, but you don't explode. Okay? That's because the reaction rate is just different. Okay? Covalent bonds take a lot longer to break apart than do ionic bonds. We're moving on. All right. Carbon, a group 14 element, has 4 valence electrons requiring 4 bonds to satisfy the octet rule. Now, typically what happens is we get chains of molecules here. And I'm going to throw this out here. I do go off book a lot in this chapter. You will want to at least skim your book because I may miss a couple things. Okay? So just mentioning that, not while I'm teaching. Okay? Just outside of class, you may need to skim it. Some of your homework answers may not have been discussed in class. Just be warned. Again, this is a very dense topic, and I've got 2 weeks. Okay? So that's what we're doing here. All right. So anyway, I'm just mentioning it because I just realized I haven't read anything out of the book yet. Anyway, so hopefully my notes the first time around were good. All right. So you'll notice that they have open chains. They can be in a branch chain. They can be in a ring. All of these things have different names. We'll talk about them more later. Just know that for now, all this stuff can happen. Okay. They can also double and triple bond just like anything else, further adding to the complexity. And we'll talk more about the nuances of that later. Now, new word you need to know for this chapter that is different from other variants of chemicals that we've talked about before. We've talked about isotopes, where they are different number of neutrons in the nucleus of atoms. We've talked about nuclides, which are basically isotopes, but when you're in nuclear chemistry. We've talked about other variations of molecules and atoms. Here's the one you need for this chapter that is going to be the most abundant. We call them isomers. These are compounds with the same molecular formula. In other words, they would have the same shorthand, okay? But they're in different branches. All 3 of these are isomers of C5H12. They all share that chemical formula. All 3 of those branches on the screen are C5H12, okay? And I only know that because it's in really fine print, like right here, okay? That's the only reason I remember the thing. I didn't count that fast. All right, so these have different structures, different arrangements of atoms, but they have the same chemical formula. We call them, again, isomers. You'll notice that iso tends to come up a lot in chemistry. It means the same but different. okay, as far as kind of how we do that. Actually, what does the prefix iso actually mean? Because I've mostly picked it up from context. I've never looked it up. I'm curious now. Oh, it means equal. Okay. So, yeah, pretty much the same but different. All right. Cool. Moving on. Now, because then we get so many chains and so many representations, we have several different models of molecules. There we go. One of which we call the space... nope, sorry. Apparently I jumped. Did I not? Okay. These right here are the structural formulas. Okay. You may remember the name Lewis structure from earlier in the year. It's essentially Lewis structure, but without the dots. Okay. Mostly because we filled all the valence electrons, so they're all bonds now. All right, so this right here is an idea of structures. We're not focusing on anything individually here, but we call these to be structural formulas. We can also have a space-filling model that's shown on the left, okay? All three of these representations are of the same molecule, okay? So we have the space-filling model. This is where you guys are familiar with the ball and stick model. We've used that a little bit in this class. In organic chemistry, you tend not to use that. You tend to use space-filling. Because technically the bonds aren't solid lines, like there's not a distinction between atoms. It's this orbital has overlapped this orbital somewhat, okay, and that's the bond, okay? Again, it's real messy, much like real life, so weird how that works. All right, so space-filling model shows the shape and bonding relationships of atoms. A structural formula shows bonding relationships, but not the shapes, although we try a little bit, of atoms. And then finally, a condensed structural formula shows bonding relationships in less space than a traditional structural formula. Instead of just saying C3H8, we would write CH3, CH2, CH3. Okay? The whole reason for that is it represents what's happening at each carbon in the chain. Okay? Without us having to draw all the lines. Okay? That's the whole reason for it. You may see that one, but all three of those are for the same molecule there. Now, one last thing we need to discuss, and we'll talk about it more later, I think. Yes, okay. And that is the idea of a functional group, okay? These are chemically reactive groups of atoms and bonds that give identifiable, there we go, getting through that word is always a challenge, physical and chemical properties to any molecule in which they are found. I'm not going to list them all in the thing. I'm not going to list them all. They're not all in the supplement. They're not all in the slides. There is a table in your textbook on page 317 that summarizes everything. Okay, I may have pictures of all the groups. Do I? I don't remember. Yeah, I do. Okay. So first up here is the alcohol group. It's just anytime you have hydroxide off to the side, okay, at the end of a chain. The reason for these groups, the reason why it matters, is these groups are what do the chemistry in organic chemistry. Most of the chain tends to remain unaffected unless it's breaking apart. Most of the chain stays the same. It's just what happens at the very end that can actually change like the whole identity of the molecule. Okay, we've seen this before where just swapping out one thing can change it. One of my biggest examples that I'd like to give is sodium is explosive if it's given the opportunity to react with water vapor. So if it's open to air at all, ever. Okay, unless you're in the middle of the desert. And even then. Anyway, you have chlorine, which as a gas will kill you. Put them together, you get table salt, which you need for life. Okay, hydrogen, extremely flammable. See the Hindenburg. Oxygen, necessary for combustion. Combine them, we use it to put out fire because it's water. Okay, it's all a matter of how things are assembled and how they're put together. Does that make sense? Okay, it changes everything. So it might look like this is such an insignificant piece of a very large molecule. By the way, real quick, anytime we have lines just branching off with nothing written, it means we're ignoring the rest of the molecule. Okay, and we're only showing it in this part because this is the part that matters. So just mentioning that there. You may also see R. R is not on the periodic table. It's a reserved character. Let me correct that. R by itself is not a chemical symbol because it's a reserved character for organic chemistry for when we don't want to write out the rest of the molecule. All right, so you guys will see that occasionally. I went on like 3 tangents there. Where was I going with any of this? Right. These are what do the actual chemistry. Okay. Again, even that little portion of the molecule undergoing a change can completely change the behavior of a molecule. The first group here is the alcohol group. Okay. And the alcohol group is just that OH at the end. It's a base. Okay. Alcohols are very useful in chemistry. They are also very useful in regular life. I don't recommend drinking them. There's a difference, okay? Alcohol is very necessary for things like sterilization. They're very necessary for things like cleaning computer hardware. They have many practical purposes outside of people drinking, okay? And I recommend that that's where it stays, but we're moving on, especially for you guys because you're all underage. All right? If I can say nothing else, this was something that I worked with a youth pastor in Albuquerque, and he's like, look, you could argue whether or not alcohol is moral to drink until the cows come home, okay? But this is a youth group. Y'all are under 21. Right now it's illegal for you, therefore it is a sin because you'd be breaking the law. Done. Ended the debate right there. He's like, and he's like, yeah, you could technically debate the other. Now, to be clear, I'm not getting into that debate, okay? Just no. Again, don't recommend it. I've watched family members drink themselves to death, but I'm not getting into that debate, okay? That's as much as I'm going to say about it. But we can't get into organic chemistry without discussing at least the alcohol group, so hence it came up. All right, moving on. This is the alkene group. Notice that it is a double bond inside. We'll talk more about it next section. We have the alkyne group, which has a triple bond. You may have noticed that all that changes is the vowel. It goes from A to E to Y. Okay? Notice it's in alphabetical order. A is 1, E is 2, Y is 3. Cool? Okay. And yes, you're going to have to come up with memory devices like that. All right. This is an aldehyde group, which has this formula. You're going to have to reference this table a lot in case you all haven't figured that out yet. All right. This is the ketone group, not to be confused with the diet keto. That's a whole different thing. All right. Actually, it might be related. You know what? Moving on. Carboxylic acid group. Okay. Notice again that hydroxide ion. You'll notice it's comes up a lot in organic chemistry, and you'll also notice there's a lot of hydrogens in organic chemistry. You may have noticed there's a lot of acid bases at play. Okay, so all that's going to come into play again. Then you have the esters, which is, there's no H, so not to be confused with ester in our class. This is the ester group. Notice the double bond with one oxygen and the branch off to another oxygen there. And you'll notice a lot of these names have to deal with oxygen, or a lot of these groups have to deal with oxygen or nitrogen, because that's typically what tends to get into polluting the chemicals. And it's not actually polluting, it's actually very useful, but like you can think of it that way. By default, it's all carbon and hydrogen. Okay, always. By default, if nothing's listed, it's carbon and hydrogen. Okay, what makes them tend to be special is their impurities, if you want to call them that, of oxygen and nitrogen, or something else. Typically oxygen and nitrogen though. Then you have the amines, which has a nitrogen, or the amides, which has a double bond with an oxygen, then a nitrogen. Okay. Again, we'll get into all these more later, but again, table 18.2, I cannot stress enough, is absolutely vital for getting this down. All right, I'm going to keep going because the next video actually starts after alkanes, so I'm not going to necessarily get through the whole thing, but we're going to talk about at least some of hydrocarbons. Now, he's already mentioned it in the video. But hydrocarbons are organic compounds containing only hydrogen and carbon, okay? Hence the name, hydrocarbon. That's all that's in there. Okay, anyway. Table 18.3 on page 318 gives you those prefixes. 1 is meth, 2 is eth, 3 is prop, 4 is bute, and then after that it's normal pent, hex, hept, oct, non, dec, and so on, okay? Everything else after that, it's the first 4 that are different. We never say quad, we never say tri, we use meth, eth, prop, and bute. Okay? Those are the main 4 that you really have to study. Everything else is what you remember from geometry. I don't know why it has its own. I'm sure there's a reason. I didn't have time to look it up. We're moving on. All right? Now, you also need to know that there's the idea of cyclic or acyclic. Okay, remember alpha negative. It happens to a lot of words. If you're not familiar with that term, that's a reference to putting the letter A at the beginning of something to say not. Okay, so we call it an alpha negative because it started in Greek, I think. Don't quote me on that. We're moving on because this is not an English class. All right, so cyclic means you have a ring, a cycle. Okay, in other words, you have carbons all in a ring together. So you'll notice the last one is cyclic. The other 2 are acyclic. Okay, While the middle one branches, you'll notice it never returns upon itself. Does that make sense? That's the key. It has to return upon itself in order to be considered cyclic. Okay, again, only the carbons. You're not looking at the hydrogens here. Okay, make sense? Cool. You guys are going to have to study a lot. I'm sorry. It's the nature of it. All right, now, there are three main key bonds that you can have between carbon atoms. If you have a single bond, which is the one we consider the most, we call that an alkane. Again, alkane, single bond. It has an A in the middle. Okay? If it's cyclic, we label it cycloalkane. Okay? We just add cyclo in front. Good? If it has two bonds, we go down to the next vowel, E. So alkene. All right? Make sense? Pretty straightforward. Again, if it's cyclic, we say it's a cycloalkene. Finally, if it has a triple bond, we jump straight to the last vowel that's not even normally a vowel and use alkyne, okay? I don't know why suddenly we jump to Y and not I, because it's the same sound. I have no idea. I didn't do it, okay? So it jumps to Y. That's all you need to know. So it's an alkyne. Again, if cyclic, which is extremely rare because triple bonds already take up so much bonding space, but this is extremely rare, we do label it as cycloalkyne if it were to exist. Again, you'd have to really, 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 really try, because triple bond and cyclic, no. All right, so that one's less likely to come up. All right, let's see here. Now, the general name for alkanes, alkenes, alkynes, and any similar hydrocarbon is aliphatic hydrocarbons. Now, if it's a cyclic hydrocarbon, we call them aromatic hydrocarbons, and these must contain delocalized electrons or resonance structures. Again, we'll talk more about those in a little bit, I think. Yes, okay, they have its own section, okay? So right now, this is just kind of overview, introducing you to the concepts. We're going to dive deeper into each of these, okay? So just kind of hang on. Now, very quickly, we say a chain is saturated if each carbon-carbon bond has a single bond. This allows additional molecules to be added without breaking any carbon chains. This is only true of alkanes. If it's an alkane, it is saturated. You may have seen the saturated versus unsaturated fat label on your nutrition facts, okay? The whole thing there is saturated fats have only alkanes. There's no carbon bonds to break. Unsaturated bonds have one or more carbon bonds having a double or triple bond, so you have room to break things and insert new atoms into the molecule chain. So unsaturated fat has more potential to have bonds made for it. We'll talk more about the differences later. These allow additional molecules to be added to the molecule without breaking the carbon chain at all. Okay? This is true of alkenes and alkynes because, again, you need something beyond a single bond. So, on to alkanes. All right, first of all, let's talk about, hold up. Hold on, I'm working on it. I'm trying to remember why this is here. Oh, this is me backtracking and I just didn't include it in the notes at all. Cool. All right, figure 18.6 in your books kind of shows you the progression of, I want to say it's alkanes. Yeah, the first four alkanes. Okay, that's why I'm doing this. Okay, it's been a while. All right, so the first four alkanes, the first one is methane. Again, that meth means one. Okay, ane means all single bonds between carbon atoms. Okay, now there's only one carbon atom, but don't look at that too closely. All right, so you'll notice there's no methane or methine, because how could you? Okay, so methane, we've talked about it before, mostly because of its tetrahedral structure. Okay, but we've talked about this before. So the condensed structural form is CH4. That's also its molecular form, or its, you know what I mean, the regular thing we would write. What is the chemical formula? There we go. Its structural form is written like that. Again, we studied this one kind of in depth when we were talking about the shapes of molecules. Notice the ball and stick models and the space filling model. Now, most of the time in organic chemistry, you're going to see gray be carbon, white be hydrogen. At some point, I'm going to stop labeling these things, okay? Only because that's common practice, okay? It's very common practice to not label carbons or hydrogens directly because we know that's what's there. Let's move on, okay? Because it's all the same. It's when you get a different color then you need a label. All right, so ethane, notice it's ane, so it's all single bonds, okay? Eth means 2, so there's now 2 carbon, 1 single bond in between. All right, so we have CH3, CH3 because each C has its own thing. The red is just showing you what we added since last time. All right, ball and stick model and the space filling model. You'll notice the ball and stick is more what you're familiar with in chemistry. The space filling model is more accurate to what it actually looks like. All right, moving on. You have propane. You have the condensed structural formula, which is CH3, CH2, CH3, because, again, that middle one can only bond to 2 hydrogens because it's got a carbon on either side. Again, prop means 3, ane means single bonds, so that's what we have. Okay. Now, you could also have isopropane. That's when it's bent the other way. We'll talk more about that later. All right, and again, space filling model for what it actually looks like. And then finally, butane. All right. We have CH3, CH2, CH2, CH3. Notice again, we're just adding another carbon in there. Butane, again, but means 4, ane means single bonds. Y'all getting the idea here? Okay, it has its own language, it has its own grammar. You kind of just have to pick it up. Okay, so the more you work with it, the better it'll be. So alkanes are aliphatic hydrocarbons, see the previous definition, containing only single bonds between carbon atoms, also known as the paraffin series. Okay, the paraffin series is really the new bit of information. We've already discussed everything else in that definition. All right, they have the basic structural element of CH2 with an additional hydrogen on either end of the strand, okay, which makes sense. Finally, they have a general formula of CnH2n plus 2, okay? In other words, however many carbons we have, there's twice as many hydrogens plus 2 because we have to end cap the thing, okay? That's why. Now, if we have a branch of it and it's not the main molecule, we call it an alkyl group, okay? That YL means it's a branch. It's not just the main string, if that makes sense. So here, I'm not going to show the animation because we don't have time and I don't have it pulled up. But methane, that one of those hydrogens, if that comes off and it bonds to a larger hydrocarbon, such as butane, okay, we can get a methyl group, okay? It's a methane minus a hydrogen, and that gets inserted into the butane in place of a hydrogen. This is how most organic chemistry works, is we take off a hydrogen, put something in its place. All right? Or we work with an end cap with a special form. We'll talk more about that later. That's the bell. Rats. Okay. So you'll notice we have the methyl group, so it becomes methyl butane. Okay? Butane doesn't lose its identity. It just has something added onto it now. All right? Make sense? We good? Cool. All right. We'll pick up there tomorrow. Actually, tomorrow we'll start with the video over alkenes and alkynes, and then we'll get back into this topic. All right, I'll see you guys later.